characterizing. So the majority of research focuses on characterizing and predicting the mean of behavior and cognition. So things like group or individual means, or mean differences, perhaps, things like t-tests, ANOVA models, changes over time in means. So even the fanciest of most growth models tends to focus on either group level or individual means and change over time in those means. But sort of this sole focus on modeling mean levels can miss an important other source of individual differences in behavior and cognitive performance, and that is variability. So intra-individual variability. So the variability within a person in their responses or their cognitions across time. And not to be too hard on us as a field, but until recently, this limitation has been driven both from a theoretical perspective, but also the lack of methodological tools that could predict variability directly. Although these sorts of limitations are being overcome by more recent methods, one of which I'll focus on here. So what do we mean by variability, and why might it be different than focus on the means? So here we have two sort of exemplar individuals, both of whom have the exact same mean response time. So response time is on the y-axis, and some number of trials is on the x-axis. And so these two individuals sort of hover around the same mean level of response time performance, but you can clearly see that the person on the left is very consistent, low variability in their response time. They tend to respond about 2.1 seconds every single time. There's sort of this narrow band that they fluctuate in. And the person on the right, by contrast, has a lot of variability. So sometimes they're responding very quickly, less than 1.5 seconds, and other times they're responding very slowly, so more closer to 3 seconds. And they don't sort of have that narrow, consistent band of performance. There might be several reasons why we might expect that these two individuals might differ, even though they have the same mean performance. So some might have sort of intrinsic mechanistic explanations. They might range from things like experience. So perhaps the person on the left is an expert at this task, and they know that they can't respond all the time as quickly as humanly possible. You just can't sustain that level of performance. So they're going to slow down a little bit, but be able to respond in the same sort of time window across the entire task. Whereas the person on the right might be less experienced, and so they're always trying to go as fast as possible, but you just can't sustain that. And so they sort of run out of some performance capacity, and that leads to variability. It might also be some sort of neurobiological difference between these individuals, which is something we'll explore later on in this talk. But there might be sort of intrinsic mechanistic reasons why there might be differences in variability, despite no difference in the mean. Another reason we might be interested in variability is that this sort of performance inconsistency might interact with some sort of external factor, some sort of environmental input. So in this task, maybe the task is constrained that if you don't respond within 2.5 seconds, the task moves on, and that trial is counted as a failure. Well, for this low variability individual, they're never going to sort of be dinged by that failure point. They're always going to respond fast enough to receive credit for that trial. Whereas the person with high variability will often sort of miss that failure point. Of course, this is just a very simple reaction time task, maybe low stakes, but you could imagine sort of this in some educational context where perhaps variability in academic performance might mean that an individual will fall below some threshold for either advancing in academic grade or perhaps being moved into some sort of special accommodations situation. And so this variability can, especially when there's sort of these natural cut points that exist in the external environment, might lead us to be more worried about this high variability individual compared to the low variability individual. So hopefully that's convinced you, at least initially, of the importance of considering variability in addition to mean performance. We're not at any point going to say that mean performance is not important, but rather that variability is additionally important. So similar means do not necessarily reflect similar profiles of repeated performance. What we focused on here is consistent versus inconsistent performance, so that variability component. But as we'll see later in the talk, there can be other more complicated aspects of performance that we might want to consider that will differentiate people who otherwise have the same mean. And understanding potential causes of consistent versus inconsistent performance, that variability component, can help build better causal models of behavior. So limits on response time versus attentional processes might be one instance. So is there that capacity difference? You as an individual cannot respond more quickly versus something like attention, where your capacity to respond is preserved across time, but it's some ability to pay attention. Sometimes your attention is very sharp and you can respond sort of faster than average even, whereas other times your attention is wandering. And so that limits your ability to respond in a speeded way. Another reason why we might be interested in sort of these potential causes of consistent and inconsistent performance is that variability actually impacts the reliability of the mean, the thing that we're more normally interested in. And that's because in a smaller number of trials, a more variable individual is likely to occasion variability in their mean performance, just because we sort of randomly sampled them and their sort of range of performance globally is wider. And so we can catch you on a worse day or a better day, and that might influence the reliability of your individual mean across measurement occasions. And that might be important, especially for things like aging, where we might be interested in decay of performance, and we don't want to suggest that someone has sort of globally decayed if we just happen to catch them on a bad day or something like that. Okay, so that's sort of variability as a construct by itself. What we might be interested in variability across development. So across the adult lifespan, reaction time specifically displays this sort of Nike swoosh effect. And despite our best efforts, Nike declined to fund this work. Although I was really hoping for some nice athletic gear. I run, and so I can always use free Nike stuff, but they're not as interested in that marketing opportunity, unfortunately. But what we mean by this is that there are sharp improvements in early decades in life, followed by sort of protracted slowing over aging. So, in the prior decades of our lives, we got fast relatively quickly, in the 10 to 20s, and then we've all sort of transitioned past the point where we're getting any sort of faster, and it's just bad news from here, where we're all going to sort of get slower over time in our reaction time. And this is across a number of different tasks. We sort of see this same sort of swoosh effect, where there's an inflection somewhere around 20s and 30s. There's some initial evidence that variability follows a similar developmental pattern. So this is with the intra-individual standard deviation. So essentially just taking the standard deviation of each individual's responses. This is a computed measure, and we'll talk a little bit more about the distinction between these computed measures and what we'll use in the current study. But again, we see sort of this sharp decrease in variability early in life, followed by sort of protracted increases. So just to depress you a little bit more, there's sort of an inverse pattern with cognitive abilities, where we see sort of sharp increases in the scores on things like crystallized and fluid intelligence, again, up until around 20s, 30s, and then it's downhill from there, suggesting that these two measures, or these two kinds of measures of performance may sort of be reflecting similar effects, sort of underlying effects going on in the brain, where we're seeing this reduced ability to respond quickly and consistently, as well as reduced capacity in these sort of higher order cognitive measures. Okay, so if we want to step back and think about what some of those brain mechanisms might be that are contributing to these effects, one of the best candidates we have is the white matter. So white matter tracks transmit signals between brain regions via insulated, biologically myelinated fibers. So while this is a somewhat imperfect metaphor for all sorts of reasons, you can think of it broadly like a copper wire, where we have some direction of signal conductance that we want to transmit down, and we insulate in order to prevent leakage sort of perpendicular to that direction in order to preserve the signal across longer distances. And on a biological level, that's generally the role of the white matter tracks. There are 10 broad tracks that we're interested in, here visualized in 3 dimensions. We will not necessarily focus on individual regions with individual hypotheses per se, but think about this as sort of a global hypothesis related to all the white matter tracks. So the mechanism that relates to variability is that theoretically, we would expect that impairments in this insulation, right, this ability to propagate signals in the chosen direction and prevent them from sort of leaking, impairments in that ability is going to lead to more inconsistent signal propagation, more variability. And something that just happened to me while I was in the US, because in the southern US, we'd have no idea how to deal with any sort of frozen thing that falls from the sky. I was, at home with my friend, and we experienced a brownout where a transformer blew in the middle of town, and we would get these sort of dimming of the lights. Sometimes it would go off for a minute or two. So it's not a blackout. We're not getting no signal from these sort of impaired white matter tracks, but there's a sort of intermittency in how much electricity we're receiving. And that's how we can think about this impairment in the insulation will lead to sort of inconsistent behavior in the same way. I think there's no better joke, I think, for Europeans than Americans dealing with snow in the southern US. I think it's incomprehensible to anyone outside of there, but it's true. Anytime more than a single snowflake falls, we just lose our minds. But broadly, this is a lower signal to noise system, right? We're getting less of the signal we care about being propagated here, some sort of motor evoked response, and we're getting more noise. So we can also build on some prior works that's going to suggest this mechanistic link between white matter and variability, which has showed that higher fractional anisotropy, which is a sort of fancy word for the ability of these fibers to direct water molecules down them as opposed to perpendicular to them. So it's in the same way that the signal that we've been talking about, this fractional anisotropy does this as a measure of the movement of water down tracks, white matter tracks, but you can sort of think of it as the same sort of signal conductance. And you want more directionality and less diffusing sort of perpendicular to the white matter track. But higher fractional anisotropy has been related to faster processing speed and better cognitive performance overall. And in clinical samples, specific white matter injuries, so things like multiple sclerosis, white matter hyperintensities, has been related to more variable performance. And it's especially nice, I mean, MS is of course a horrible disease, but it allows for this really nice testing of this hypothesis because there's sort of a graded response of the more severe the autoimmune response is, the more degraded the white matter insulation is. And so you can kind of get a graded response as opposed to something like a lesion where you're just missing chunks of the white matter. And there are sort of other non-specific effects of that. So limitations of the work so far, and sort of where we think that we can come in with these new tools, is that most of the work has been done, as is common in neuroimaging samples, in quite small normative samples or in clinical populations. And so we wanted to be able to do this in a large normative sample to look at sort of the generalizability of these effects. The other is that very often they rely on observed measures of variability. So something I mentioned earlier about the intra-individual standard deviation and the intra-individual coefficient of variation, which is just the ISD divided by the mean of performance, are all calculated on the data and are treated therefore as observed measures themselves. One of the issues, and the one that we're most often concerned with, is that they're confounded with mean performance, especially in sort of bounded data like reaction time, where there's a pronounced floor effect. You can't sort of push faster and faster responses. There's sort of a biological limit imposed there. They can be inflated by unmodeled components of performance. So things like trends. Do you get systematically better or worse over time in a task? And then autoregression, which is sort of the temporal dependency of a current trial on a prior trial. All of these inside the time series will sort of show up in this observed measure of variability, because we're not sort of pulling apart those unmodeled components when we calculate these measures. And if you're not totally clear, I mean, I think trends are somewhat intuitive, but if you're not totally clear on autoregression, we'll sort of have an exemplar that shows what higher autoregression sort of does to a time series. So they're also, and this is an additional problem, is they're treated as fixed and known versus being estimates of effects. And so when we use them in later analyses, we're not sort of propagating the uncertainty in them that we would like to. And finally, they are by themselves calculated as measures of variability. And we might also want to be able to model the mean and these other components of performance simultaneously, as well as predict them simultaneously. And so using these observed measures doesn't allow for that. And so we think that a model-based way that we'll show with the dynamic SEM models is better theoretically and sort of statistically. Okay, so the current work. So we're going to pull data from the Cambridge Center for Aging and Neuroscience, the CAM-CAN dataset, which is a large adult lifespan cohort out of the UK. And in this dataset, there are about 2,700 individuals who completed behavioral sessions. And then a subset of those, about 700, completed a neuroimaging sample. And it's going to be ages 18 through 102, so quite a wide age span. And so here, just in gray, is the distribution of ages for the behavioral sessions, and then here under in red is the distribution for the neuroimaging samples. So covering quite I just hope to get to the end of this age range. It's quite remarkable, the 102-year-olds coming into the lab to do these sorts of tasks. So the task that we're going to use for this is a very simple reaction time task. It's nothing more than participants have 4 cues. They're cued to respond with a given finger, and their instructions are just to respond as fast as possible. And so it's there are no incentives, there's no additional complexity. It's just a simple reaction time. There are 50 trials, so they do this repeatedly. And here's a subset of 500. And you can see that there's a reasonably pronounced floor effect. You just can't respond infinitely faster, but then there's dispersion. And there's sort of individual variability in where people are on a given trial. So this is just the raw data being plotted here. We haven't imposed any sort of model to it. Okay, so this is a lot, but we're going to walk through it sort of piece by piece. But this is going to be the dynamic structural equation model that we used sort of to fit this data and test the hypothesis of the neural noise. So we can start with looking at the within person model here, surrounded by the dashed bar box. And we're going to model reaction time as a function of the trial, so the current trial. So this is going to be how we look at trends in the data. So rather than detrending sort of before modeling, we're going to do it as part of the model itself. And then the dependency of current reaction time, so RT at time t, on the prior trial. So if you responded previously, if you responded quickly on the prior trial, do you respond quickly on the current trial, or do you respond more slowly? So this captures that effect there. And then we're going to model the intercept and the intra-individual variability of reaction time. So that's the within person model. So that's intra-individual difference. But then we're going to use a second level, the between person level, to model inter-individual differences in these processes at the trial level. So we've color-coded things to sort of keep track of which effects we're talking about. Here in red is mu, which is just going to be inter-individual variability in mean performance. So it's level on average. So that's sort of the traditional thing that we're interested in. Psi in green is going to be inter-individual variability in intra-individual variability. So differences between people in how much they're dispersed around their mean of reaction time. We're going to get the trend in blue, beta t, and then phi, which is going to capture that autoregressive effect here in purple. And the dashed arrows just point to which components of the within person model is being expressed here at the between person level. Because it's a structural equation model, we can then bring in predictors. So here age and white matter fractional anisotropy as simultaneous predictors of all of the 4 components of behavior. And then they'll be allowed to covary as exogenous variables. And so this is going to be how we test that neural noise hypothesis. Can we first separate out these 4 components of behavior? And then what are the unique influences of our covariates on each of them? And we hypothesize that reduced white matter specifically is going to be related to poorer performance characterized by higher means, so they're slower, and greater variability, so they're less consistent. So that's diagrammatically, this is just the equation form of it. We're going to take the log as is canonical with reaction time data, but we're modeling it as a function of the intercept, mu, the autoregressive effect phi, the trend beta t, and then the residual, which is normally distributed with a variance of psi. And then we'll predict in the conditional model each of those components with our white matter and age covariates. Okay, so this is a lot. What would this mean practically to be high, low dependence, standard mean, and pretty low variability? In red, we have a high mean person. All they are is slower. So this is probably the easiest one. They're just slower. Everything else about their time series is sort of characteristically the same as the reference. High psi is like what we saw earlier. I've changed the mean, obviously, just so that we can visualize them. But the main difference is that there's just greater dispersion. A high trend, that's also relatively intuitive. They're just getting worse over time. This person is slowing down systematically. And then the high phi component in purple is the autoregressive effect. And you can see that while the reference and frankly all the other time series have pretty low dependence between adjacent trials, they have quick periodicity between the fluctuations. High autoregression induces these sort of slower waves in the data, where you can see that there's higher dependence. If you're fast on one trial, you tend to be fast on another. If you're slow on one trial, you tend to be slow on the next. And you can see how this induces variability. I don't actually increase the variability parameter here, but just by nature of the sort of slow waves, there's more variability in it than there is in the reference. And so this is one of those cases where these higher order effects sort of masquerade as variability if we're not separating them out. Okay, so the actual results, not just simulated references. So the first thing we did is compared the model, an unconditional model, so we don't add in the predictors, that have fixed effects of our 4 different components versus random effects. Unsurprisingly, model information criteria always favor the random effects. It's not surprising that we can't characterize all 2,700 individuals with a single mean, a single variability parameter, and so forth. But we did that check. And then in the unconditional model, we showed that there's significant between person variance in both the mean level and within person variability in performance. So we are capturing individual variability in each of these components, as well as those two. So these two are sort of more exploratory. Our main hypotheses are related to mean and variability, although we think it's important to control for the trend and autoregression. There's just much less work done on it, so it's harder to have a more specific hypothesis. Mean, variability, and autoregression are all positively correlated. So that's this cell, and then these 2 cells. And then they're all negatively correlated with the trend in these data. But what's interesting and quite nice about the model-based approach is that it's not that the mean and the variability components are uncorrelated, they're still correlated about 0.4, but that they're less correlated than if we had just taken computed measures and correlated the mean and the ISD here, suggestively correlated at 0.666, which I think is the worst correlation one can have, because you run afoul of the holy stats gods, I believe. But it's a nice utility of the model-based approach is that we're doing a better job of separating these components of performance than we would be by just using computed measures. Another just sort of glimpse into some difficulties with the computed measures. So here we predicted the calculated score that we would derive from these data by our factor estimates of each of the 4 different components in just OLS regression. And for ISD, we do a pretty good job of explaining variance in that measure, about 0.9. And the strongest influence is indeed psi, so that's a nice validity check. But there are significant influences of both the mean, the trend, and the autoregression, suggesting, as we expect, that these computed measures are somewhat contaminated by other measures of performance. Somewhat troubling, the ICV seems to not have a good theoretical relation to the model-based approaches. So it's most strongly related to the mean, but negatively. And it's also negatively related to the psi factor. And so we're not entirely sure how to reconcile the difference between these two. That's something that we're interested in thinking more about. But it does seem that at least sort of globally, both of these measures have some confounds that we might need to be worried about, suggesting that the model-based approach has some nice advantages. So when we do bring in our predictors, both advanced age and reduced white matter predicted poorer overall performance. And so that means that age positively predicted both the mean and variability on an individual level. And so older individuals are both slower and less consistent. And the same is true for the white matter tracks. So here, this is the anterior thalamic radiation, but these effects are relatively consistent across tracks. There's a negative relationship such that poor fractional anisotropy is related to slower and more variable performance. Neither of them are related to the trend or to phi. So we're just focusing on our main hypotheses here. So if we plot white matter integrity against the predicted variability across the 10 different tracks, there's a negative relationship in all of them except for in the Sing hip track. So it's directionally similar, but does not reach significance. But this is pretty significant or consistent evidence that white matter fractional anisotropy is having or is negatively related to performance. And then this is just for age. So we have the positive effect of age on the mean and variability here. And then these two effects are also not significant. Okay, so broadly, we found support for a neural noise hypothesis of behavioral variability where impaired white matter in microstructure is related to greater variability as well as slowing of mean performance. The white matter effects hold controlling for age, so it's not just sort of age effects purely. There's also sort of the specific role for white matter. And from a modeling perspective, we were able to model both the mean and the variance within individuals simultaneously without any convergence issues, despite a reasonably high correlation of the observed measures in the data. We also got additional information from modeling the trend in autoregressive terms. So even if the effects weren't significant, it's important that we're teasing out the variability associated with those terms. And we hope that DSEM and other tools like it provide an exciting avenue for future investigations of individual differences, focused not just on the means, but also on the important variability differences. So I just want to thank everyone in the LCD lab, Rogier for hiring me and being a wonderful mentor, and then other members of our lab, the Radboud and Donders, and then the CAMCAN, the Cambridge Center for Aging and Neuroscience, for providing the data. And thank you, all of you, for your attention.